Welcome to video 3 of 4, Fixed Hit or Practical Regularization. Early Stopping, the Free Regularizer, Bagging and the Ensemble Family Boosting, Stacking Voting, Dropout Training with Random Amnesia and Why Sabotaging Your Own Network Makes It Stronger, Adversarial Training, the Invisible Attacks and the Defense, and the Tangent Methods. This is the toolbox at full power. Let's go! Procedure bucket now in the cheapest regularizer in existence, early stopping. The problem it solves: how many epochs? Too many overfitting? Too few underfitting? Unit 2's toast burning in slow motion. The algorithm: 5 steps. Train with a generous number of epochs, 1 or 200. After each epoch, check performance on the validation set. Track the validation error. When it starts rising, the model has begun overfitting. Stop and keep the weights from the point where validation error was lowest. In practice you'll meet this as a patience setting. Keep training until validation loss hasn't improved for, say, 10 epochs, then restore the best checkpoint. Why is stopping a form of regularization? Limiting training time limits how far the weights can travel from their small initial values, mathematically cousin to weight decay, and it costs nothing. That's why it's in virtually every real training run on Earth. Ensemble methods: the wisdom of crowds, engineered. First and most famous, bagging. An ensemble combines multiple models on the same problem, merging their predictions to beat any single model. Bagging: bootstrap aggregating in 3 steps. 1. Create multiple datasets by bootstrap sampling, random sampling with replacement so each dataset is a different remix. 2. Train a separate model on each. 3. Combine majority vote for classification, averaging for regression. Why it works: the jelly bean jar. Ask one friend to guess the count, they're wildly off. Ask 100 and average, shockingly close. Individual errors are random, so they cancel. In our Unit 2 language, bagging attacks variance directly. The celebrity example: random forest. A single decision tree overfits high variance. A forest of bootstrapped trees, voting. Strong and stable, still the go-to baseline in classical machine learning. Bagging has siblings: 3 more ensemble strategies. Boosting: models train sequentially, not independently. Each new model focuses on the mistakes of the previous one. Train, find the errors, train the next to fix them, combine all. The famous algorithms: AdaBoost, gradient boosting, XGBoost. Boosting reduces bias and reaches high accuracy but can overfit if uncontrolled. Stacking: combine different model types, a decision tree, an SVM, a neural network, and then train a META model that learns how best to blend their predictions. A model whose inputs are other models' attempts. Very powerful, it exploits complementary strengths. And voting: everyone predicts. The answer is chosen by vote. Hard voting takes the majority class, soft voting averages the probabilities. The exam contrast to burn-in. Bagging: parallel independent, cuts variance. Boosting: sequential, error-focused, cuts bias. And a fun fact: with Kaggle solutions are almost always stacks of many models. And now the flagship regularizer of deep learning, Dropout Training with Random Amnesia. The mechanism: during training, randomly drop set to 0 a fraction of the neurons, fresh every iteration. With a dropout rate of 0.5, every neuron has a coin flip chance of vanishing on any given step. Why on earth does sabotaging your own network help? The football team analogy: random players sit out every practice. Nobody can hide behind the star teammate, every player is forced to become individually competent. In network terms, no neuron can rely on specific partners, so each must learn independently useful features. Co-adaptation broken. And the deeper theory: from the source, within neurons, Dropout implicitly trains 2to the power and different thinned networks, a different one each batch, all sharing weights. It's a colossal ensemble, bagging without paying for in models. At test time, the full squad plays. The exact mechanics: 4 phases. Next slide. Dropout's 4 phases, the mechanics that exams probe. Phase 1: training selection. Each iteration, randomly select neurons to drop, per the dropout rate. A fresh selection every single batch. Phase 2: forward pass. The network runs normally, but dropped neurons output 0. Their activations simply don't exist this round. Phase 3: backward pass. Only the active neurons receive gradients and updates. The sleeping ones sit this round out entirely. Phase 4: test time, and here's the subtle part. dropout switches off, all neurons participate, but the weights are scaled by the dropout rate, Y scale, expectation matching. A neuron that was present only half the time during training delivered half the expected signal. At test with everyone present, we halved outgoing weights so totals match what the network learned to expect. Typical rates 0.5 for hidden layers, 0.1 or 2 for inputs. And the classic real-world bug, forgetting to disable dropout at inference in PyTorch. That's what model.evil is for. Now for regularizations, action movie adversarial training, defending against invisible attacks. The threat, adversarial examples, inputs almost identical to the original, that fool the model completely. The legendary demo, a panda photo, plus a whisper of pixel noise a human cannot see, classified as a GIBBON, at 99% confidence. How are they made? The FGSM formula on screen, fast gradient sine method. Read it carefully, the gradient of the loss, with respect to the input, not the weights, the image, same backpropagation machinery, aimed at the pixels, finding the most damaging invisible nudge. Epsilon caps the perturbation size and L infinity constraint unit 1's worst case norm weaponized. The defense generate adversarial examples during training, include them alongside the originals, optimize the loss on BOTH. The model learns to hold its answer under attack. Why it's in this chapter. Adversarial training is data augmentation with worst CASE examples, and it matters. Stickers on stop signs have fooled real traffic classifiers. Robustness is safety. The final technique family, the tangent methods. First, tangent distance, a smarter way to compare images. The problem, two handwritten trees, one slightly rotated. Compare them pixel by pixel with Euclidean distance, and the distance is large, because every pixel moved. Yet any human sees same digit? Raw pixel distance is blind to harmless transformations. Tangent distance fixes this by allowing small transformations before measuring, rotation, translation, scaling, shearing. Generate slightly transformed versions of one image, take the minimum distance to the other, align first, the compare. The efficiency trick behind the name, instead of actually generating every transformation expensive, it uses a tangent, a linear approximation of the transformation curve. Fast and robust, two small variations. Its home turf, handwriting recognition and pattern classification. You do this naturally when comparing signatures, mentally rotating and rescaling before judging. Tangent distance teaches that reflex to the machine. Two siblings complete, the family tangent propagation, and the manifold tangent classifier. Tangent prop moves the idea from comparison into training, to find the transformations that shouldn't matter, rotation, shift, scaling. Compute their tangent vectors, then add a penalty to the loss for any output change along those directions. Loss equals classification error plus lambda times an invariance penalty. The network is literally fined for being sensitive to harmless changes. The manifold tangent classifier goes one step further. Instead of us specifying the transformations, it learns them from data, the key image, straight from the source, a sheet of paper lying in a 3D room. The room is pixel space, the paper is the manifold, the low-dimensional surface where the real data actually lives. MTC discovers the paper's directions, then penalizes sensitivity along them. The comparison for the exam, tangent distance used during comparison, tangent prop used during training, and the unifying sentence for this entire part, augmentation, noise, tangent prop, MTC, all of them are ways of telling the model WHICH variations don't matter. Quiz 3 Dropout mechanics? This one catches almost everyone the first time. During training with dropout at rate 0.5, what happens, and what changes at test time? Half the weights are permanently deleted. Test uses the smaller network. B. Each iteration randomly zeroes about half the neurons. At test, all neurons are active, with weights scaled to compensate. C. Neurons are dropped only at test time, to speed up inference. D. The learning rate is halved every epoch until convergence. 2 checkpoints, neurons or weights, and what happens at test? Pause and lock it in. The answer is B. During training, a fresh random subset of neurons, their activations gets zeroed every iteration. A different thinned network each batch, 2 to the n subnetworks, sharing weights. The weights are never deleted. Option A inverts that. At test, dropout switches off. everyone plays and the weights are scaled by the dropout rate. Why? A neuron present half the time in training delivered half the expected signal. Test time weights must match that expectation. Option C is backwards. Dropping at inference would just make predictions worse. Option D describes a learning rate schedule, nothing to do with dropout, and the practical takeaway that will one day save you an afternoon of debugging. Model.eval in PyTorch exists precisely to switch dropout off. Forgetting it is a rite of passage. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.